Okay, now for the second question, we are looking at the same motor, but now we are taking out the compensating winding. Okay, so the same motor without compensating windings. Now we know that when there is no compensating winding, the flux will be reduced with the increase in load. Okay, in the previous example, we talk about when the shunt DC motor has compensating windings in which the flux remain constant. Okay, now when the flux reduced with increasing load, with the absence of compensating winding, we will have to consider what we call a total magnetomotive force in the machine that are um, uh, capable, okay, of producing the amount of flux inside the machine. Because now when flux is reduced, it means that even though with the same amount of current that we supply, we will get much lesser magnetomotive force and therefore much lesser flux. Okay, all right. So if you take a look at this example, everything else is the same, except now it says that the armature reaction produces a demagnetizing magnetomotive force. So demagnetizing means you will minus this amount of 840 ampere turns when there is a current, okay, flow inside the armature. Okay, so the armature reaction happens because we don't have compensating windings, right? So we can see that the magnetization curve is also shown here, and it is taken at a speed of 1200 rpm. Okay, I need to emphasize here that the magnetization curve is not the same. It's not so basically for every magnetization curve, it is plotted at certain speed. So different speed, we will have a different value of voltages there. Okay, but the shape will be much less the same. Okay, so for example, if we take a look at magnetization curve, for example at 1200 rpm, okay, it will look like this. At 1500 rpm, for example, it will look like this as well. It's just that the value here will be different, or will be larger than the value at 1200 rpm. So we must always refer to at what speed this magnetization curve is drawn at. Okay, all right, so go straight away with the question. Find the motor speed when the input current is 200 ampere. And we know that the armature current happens because we have the so the armature reaction happens because we have armature current goes inside the machine. All right, so when this happens, we know that we will have to consider the armature reaction that influence the amount of flux inside the machine. Okay, so when the input current is 200 ampere, we know that the armature current is the line current minus IF, right? Because this is shunt, so it is 200 ampere. So IF is a VT divided by R adjusted plus RF, or it is VT over R total. It's the same thing. Alright, so VT is 250 divided by, it's the same value, 50 ohms. So we'll get 195 ampere. Okay, this is calculated from the same way as we've done that before. Alright, and the internal generated voltage that we have is simply VT minus IA RA. And why we minus IA RA? Because when there is a current flow inside the machine, we know that there is a voltage drop at armature resistance, right? When there is no load, there is the IA is equal to 0. There is no voltage drop there. But when there is a current flow, then obviously we will have voltage drop at IARA. So that's why we need to minus. So VT is now simply 250 minus 195 times 0.06, and EA will be 238.3 volts. Okay, Now, when there is an armature reaction, we know that the amount of flux is much lesser. Okay, so how can this be interpreted in the amount of speed that will change? Okay, so by theoretically, we know that from the lecture, with the armature reaction you will get larger speed, okay, in comparison with the motor that has no armature reaction. So right now, because of the weakening of the flux, right? Okay, so how can that be translated into how can that be computed? Okay, so with a demagnetizing magnetomotive force, the effective shunt field current will now be different. Okay, so field current here is basically 5 ampere, right? Okay, if there is no armature reaction, field current is 5 ampere. Now, because there is an armature reaction, the effective field current, we put it star, is not 5 ampere anymore. You will have to minus the armature reaction, which happens, okay, inside the machine. So because this unit is ampere, right, and this unit is ampere, and armature reaction is actually ampere turns. So to get ampere, we'll have to divide by turns, and the turns here is the field, the number of turns at the field winding. Okay, so the field current is 5 ampere, and the demagnetizing magnetomotive force is actually 840 ampere turns divided by the field winding has 1200 turns per pole. Okay, so it becomes 4.3 ampere. Now this is the amount of what we call effective field current. Okay, so the comparison is with armature reaction. The effective field current is actually IF minus the armature reaction divided by the number of field turns. Okay, so we will get lesser. So IF star is less than IF. Now, without armature reaction, the effective field current is simply IF, because when we don't have armature reaction, this goes to 0, is simply IF. So effective field current is actually the field current itself, okay, when there is no armature reaction. Alright, now what is the use of knowing the effective field current? Okay, so if we take a look at this magnetization curve, okay, at the bottom is actually a field current. Okay, I'm sorry, I cropped out the caption here. So the manipulating variable, or the x-axis, is actually a field current, and at the y-axis we have open circuit terminal voltage. Okay, alright, so I will explain what it is after this, but we know that right now, if we have 5 ampere, okay, if we have 5 ampere, obviously the open circuit terminal voltage is 250 volts. Alright, now we have 4.3 effective field current, and the open circuit terminal voltage is 233 volts. Okay, so 233 volts. So it's different. Okay, so if we have IF equals to 5 ampere, we'll have open circuit terminal voltage, VOC, as 250 volts, and if we have IF equals to 4.3, the open circuit terminal voltage is 233 volts. Okay, what does this means? Okay, so open circuit terminal voltage means what? Means there is no current flow. Okay, current flow inside the machine. Okay, so that's why we have an open circuit. So this corresponds to what? To a no load. Okay, to a no load voltage. So basically, if we have some sort of IF equals to 5 ampere. If the effective field current is actually 5 ampere, the voltage that we have is actually 250 volts. Alright. But now, because the effective field current becomes 4.3 ampere, even though we fed 250, because of the weakening flux, we will have, instead of 250, we will have a terminal voltage of 233 volts. Okay, so this is actually equals to the terminal voltage that we have. Okay, so therefore, we know that the internal generated voltage of 233 volts is basically obtained at a no load speed, right? Because this is open circuit. Remember, there is no current flow. So this is obtained at n equals to 1200 RPM. Okay, alright. So, and it is also confirmed by the question itself. The magnetization curve shown is taken at a speed of 1200 RPM. Okay. Since the actual internal generated voltage is not 233, okay, we know that from our calculation, the internal generated voltage is 238.3 volts. So obviously, it's higher than this internal generated voltage that we have. Okay, so basically we will have a different speed, right? So the actual operating speed, therefore, we will be using the same equation that we used in the first place. Okay, so EA at no load, okay, and N at no load, and then EA that we want to know, okay, and the speed that we want to know. Okay, so EA at no load here, we know it's 233 volts, right? And then the speed at no load is 1200 RPM. Okay, and then EA that we have now is 238.3 volts, and the speed is what we want to know, right? So as we calculated, the speed now becomes 1227 RPM. Right? Okay. So I hope this doesn't confuse you, especially this term, okay? The open circuit terminal voltage. So open circuit means there is no current flow. No current flow inside the circuit. Okay? So when there is no current flow inside the circuit, remember that this is, we have EA, and then we have RA, and then we have R total here, right? The field. And then we have a terminal voltage here, right? So if there is no current flow, okay, so open circuit means the VOC means like the open circuit voltage means there is no current flow inside the circuit, and that is the amount of voltage that we have at the terminal. Okay, so basically, if there is no current flow, we will not have any voltage drop here. So this line only have EA, and this line is VOC. Okay, like this. Alright, so EA will be equals to VOC, it will be equals to VT at this point, and therefore that's why we we read it like that from the magnetization curve lah. Okay,